Welcome back to Calculus 2. In this video we're going to be looking at managing error for approximation of integrals. So we've already looked at the trapezoidal rule and the Simpson's rule. We've reviewed them. Now we're going to look at what if they're a non-elementary integral, something you can't easily integrate. Well, can you have an idea of how close your approximation is to the actual integral? And yes, that's done by these error estimates. So we have an error estimate on both the error of the trapezoidal rule and the error of the Simpson's rule. It does require a little bit of doing to prove this. I'm not actually going to present the proof for these two, but they actually do present the proofs, or at least arguments, for why these error estimates are true on page 498 and 499 of our textbook. If you want to look at them, they're kind of interesting. But we're just going to use these. So the things to point out for the error estimate on the trapezoidal rule. So if f double prime is continuous, so you do need that, it's a continuous second derivative, and you need an upper bound on the values of the absolute value of the second derivative, that's easier than you might think, especially for a continuous function. Then your error is bounded by this quotient. Your m, which is your upper bound, times the length of the interval cubed, over 12 times your number of subintervals squared. So this will tell you if you want to bound with a certain error, like say 0.000001, well, you just set this to be less than or equal 0.000001, and then figure out what your n would have to be, how many subintervals you'd have to have that accuracy. Because if you can bound this with something, that will also bound the error. Simpson's rule is very similar, except here it is the fourth derivative. Remember, this notation is for the fourth derivative. After a few iterations, we drop the prime notation and use this because it's shorter. So your fourth derivative has to be continuous. You have to have an upper bound on your fourth derivative in absolute value. Then your error is bounded by this, which is a very similar looking expression. Also has n in it, length of the interval, in this case to the fifth power, but times m over 180 into the fourth. And this actually decreases more quickly than the error on the trapezoidal rule, because the trapezoidal rule had n squared on the bottom, where this is n to the fourth. So although the error on this for a small number of intervals might be greater than the trapezoidal rule, as soon as you get out to a decently high n, this will be much smaller, just because n to the fourth will be so much larger than n squared. So these are our two errors. Let's apply them. So here's the problem we're going to be doing. This is exercise 20 from 8.7. We're going to estimate the minimum number of subintervals needed to approximate the integral with an error less than 0.0001 by the trapezoidal rule and by Simpson's rule. So we know that the trapezoidal rule has an error that is bounded by m times b minus a to the third over 12n squared, and Simpson's rule, the error is bounded by n, we'll call this n because it's going to be a different number, times b minus a to the fifth over 180 n to the fourth. So we got to do some scratch work here first, because we need to know what m is. Oh, we do want to bound these, so I guess I'll do that. Error less than. So we want this to be less than 0.0001, less than 0.0001. Got to do some scratch work here, because we need to know what these m and n's are. So for m, we need to know the second derivative. So f of x is x plus 1 to the 1/2. Negative 1/2, my bad. F prime is negative 1/2 x plus 1 to the negative 3/2. Second derivative. This is all we need for the trapezoidal rule, but we've got to go up to the fourth derivative for this, so we might as well keep going. Let's see, that will be 3/4 x plus 1 to the negative 5/2. Third derivative be negative 15 over 8 x plus 1 to the negative 7/2. And the fourth derivative, that'll be 7 times 15 is 105, I think. Yeah. 105 over 16 x plus 1 to the negative 9/2. Quick note here, I actually made a mistake when I was copying the original problem. This was a 0, not a 1. I actually went quite a bit further, then had to come back, but just a little note here. So, now that we've found our second derivative and our fourth derivative, we look at the graphs. Already done this one here. If we look at the first one, negative 0.5. Oh, actually, that's the wrong one, isn't it? Well, if we look at our graph, we have 3/4 times x plus 1 to the, in parentheses, negative 5 over 2. Look at that graph. You can see it actually gets smaller closer to 0 as it goes to the right. So the leftmost point in the interval is going to be the highest value. So yeah, 0 is what we need to plug in, which coincidentally is very easy to plug in. So that's nice. So we got f double prime of 0. That will get us 3/4 times 0 plus 1 is 1 to the negative 5/2. So that's just 3/4. So that's going to be our m. Might as well do our fourth derivative while we're here. Fourth derivative of 0 is 105 over 16 times 1 to the negative 9/2. So that is 105 over 16. All right, that's our n. Don't think this should take too long to solve now, so I can plug this in, 3/4 there. So that'll be 3 times b minus a, or I know what b minus a is. B minus a is what? 3 minus 0, that's 3. So 3 times 3 cubed over 12. Let's see, I got my 4 as well. 4 times 12 n squared is less than 0.0001. To solve this inequality for n, the first thing I'm going to do is just flip both sides. When you have positive numbers on both sides, or negative numbers on both sides, the same sign, if you flip both sides, flip the fraction, it means you're going to flip the inequality. So that is going to be 4 times 12 is 48 n squared over 3 to the 4th, that is 81, is greater than 0.0001. Ah. There we go. I was thinking there was something wrong with that. I just forgot to flip that side. So then n squared is greater than, let's see, 81 times 1 over 0.0048. So n is greater than the square root of that. 81 over 0.0048. If we plug that into the calculator, the square root of 81 divided by 0.0048, we get 129.9. Now remember, this is going to be the minimum number of subintervals needed to approximate the interval. We don't do partial subintervals, so we need to round this up, because that'll be the minimum number of subintervals. If we round down, we won't approximate it within 0.0001. So we need, approximately, we need at least 130 subintervals. That's a lot, but it does tell you how many you'd have to do to get within this accuracy. And honestly, that's helpful to know. If you're going to do this approximation interval for an actual application, often there are constraints on how accurate you have to be. And if you attain that accuracy, you're good. Let's do it for Simpson's rule. So this is going to be very similar. Plug in our 105 over 16. I don't know what. 105 times 3 to the 5th over 16 times 180 into the 4th less than 0.0001. Flip both sides. 16 times 180 into the 4th. I'm just going to wait to do all my arithmetic till the end of this one, since these are going to be quite large numbers. Probably could do 3 to the 5th. 3 to the 5th is, what, 243, I think? Greater than 1 over 0.0001. So I think that is 10,000. Anyway, so into the 4th is greater than, let's see, 105 times 3 to the 5th over 16 times 180 times 0.0001. Then we're just going to raise that to the, I'm going to 4th root it. So in the calculator, I'm just going to do to the 1/4 power. So n is greater than or equal to, let's see here, 105 times 3 to the 5th divided by 16 times 180 times 0.0001. Alright, that should be fine for the fraction. We want to raise that to the 4th power, so I don't have to do parentheses, I'll just do 0.25, same thing. And rounding up, that would be 18. Now note, Simpson's rule requires an even number of subintervals, so if we got 17, we'd still have to round up to 18. So yeah, only 18 intervals to attain that level of accuracy with Simpson's rule, which is much better than 130. So you can see that for larger number of intervals, Simpson's rule becomes much better because of that division by n to the 4th. It's just the idea of how it approximates with parabolas, with actual curves, instead of just straight-sided figures, means it works a lot better for approximating curves. That'll be it for this video and for the section. So go ahead and work on the homework for 8.7. After this, we'll actually dig into 8.8. We'll actually be skipping 8.9, partly just because we missed a week of the semester, partly just because it's just an additional topic. In that sense, it's a lot like the Big O little o notation section in the middle of Chapter 7. So we'll go right on to Chapter 9. We won't have another test until the end of Chapter 9. See you next video.